Hi, my name is Han, and today we talk about the security of Ledger application, particularly for the case of the upcoming Zcash or shielded wallet support for Y wallet with the Ledger Nano S or S Plus and Nano X. So if you are looking at using a hardware crypto wallet such as Ledger or the Trezor X or Trezor in general. It's a really good start. Highly recommend doing that because the security of the device is much higher than if you're using an online wallet or if you're using a computer or mobile device for storing your coin. So that's a huge step forward in security. But it comes at a cost. I mean, these devices are not very powerful, definitely much less powerful than a computer, and therefore there are some security considerations to be taken could be, when you move an application to a hardware wallet. So if you have a hardware wallet, you know that these guys don't work all by themselves. They work with a companion app. So for the Ledger, it would be Ledger Live. For Trezor, it would be Trezor Suite. And they work with a companion app because they themselves, uh, by design, are isolated from the network. They are isolated from the internet and from the blockchain. So what they do is they securely store your secret keys, your cryptographic keys, and when you need to sign a transaction, when you need to make a payment, the um, the online part of the wallet, the online application, so in this case would be Ledger Live, but in our case it would be Y Wallet. So Y Wallet would be providing the ledger with the transaction to sign, and then the user will see the content of the transaction to verify that transaction is as he is expected. Then he can initiate the signature, so the signing process. And once that's done, the device, the ledger, will send the signature back to the online app, to Y Wallet, and Y Wallet will complete the transaction and broadcast it to the network. So there's some kind of partnership between the online wallet, Y Wallet in this case, and the offline wallet, which is the ledger device. So this guy here. Um, the trick here though is that the you don't want to have a malicious app tricking the hardware wallet into signing something that is malicious. So the idea here is that in the worst case, your online wallet is compromised and some code has been injected or it has been completely rewritten in with the intent to make you believe it's a legitimate app, but it's actually the result of a hacker. And then the online wallet, so the malicious wallet, will trick you into signing a transaction from with your ledger, and then instead of making the transaction that you expect to sign, it will actually either send to the wrong location or send a higher fee or do all kinds of terrible things. And the problem here is that your offline wallet, the ledger, is oblivious of the outside. It does not know what the blockchain has. Therefore, it can't verify to the full extent the integrity of the data that it receives from the online wallet. And the problem is becomes very tricky when the transaction is complex, has a lot of components, and that's the case for Zcash. Transaction is part of transactions is encrypted. It has ZK proofs or has all this stuff. And with the amount of computing power and memory that the ledger has, um, it's impossible for that device to be fully capable to form a transaction. So today we are going to discuss the design of the app of the companion app for Y Wallet, the Ledger app for Y Wallet for Zcash that will solve these issues to the extent that they're acceptable, right? And that there's no security and no chance of data loss of monetary loss. So let's start with something easier because Zcash is we don't want to jump into something that is so complicated in Zcash. So let's start with Bitcoin, and Zcash is a natural evolution of Bitcoin. So what we learn with Bitcoin will not be very different when it comes to Zcash. So we should take Bitcoin. You must be familiar already right now at this point with the transaction model of Bitcoin, which is based on UTXO. So every transaction in Bitcoin will have, I don't know if it's a good link. Not really, I haven't really prepared this in advance. Oh, okay. You can read that and probably already know about this. So the transaction will have a certain number of inputs, which contains funds that you have received previously, and a certain number of outputs, which are new recipients of your payments. So in the typical case, you would have maybe one or two inputs, and you have one or two outputs. More likely, you have two outputs because you would pay someone a certain amount, and since you can't partially spend an input, you would have an excess of money coming into the transaction, and then you will send the overflow, the excess, back to your own account, minus the fee. So that means that it's probably going to be like one or two inputs and two outputs. So four things in general. So you could imagine that this transaction is not very big. It's about 200 bytes. So if it's pretty well into a ledger, into Ledger Nano, even the smallest model. And before we talk about that, let's talk about what's the stuff that the device, the ledger, we actually perform. So we talk about the ledger signing transactions. What it signs is not the full transaction. It actually works on signing a hash, and the hash itself is calculated on top of the transaction or parts of the transaction. So the hash that the signature is applied on is it's called a sig hash or signature hash, and the way it's calculated is differs with the coins, but the purpose is that sig hash should cover all the parts of the transactions that you want to lock in place. For example, if you want to make sure that the recipient cannot change, then you make the sig hash cover the address of the recipient. Therefore, if somebody else receives that signature and tries to change the recipient, try to change the address or the amount, for example, the sig hash will be different, and then the signature will not be valid anymore. So the signature is good for a given secret key, but also obviously for a given sig hash. So it's a combination of the two of them. And the way you calculate the sig hash, it again depends on the coin, and it's very important to know that and how it's designed, uh, because as we see later, it has a huge impact on scalability and on security. So for the case of Bitcoin, the SIG hash is simplified a little bit, but it's basically uh, apply on the inputs, um, except of course the signature part and the outputs. For most of the cases, there are some types of transactions that are not exactly going to be like that. It will be anyone can pay or single, but for the mass majority, it covers everything. It covers all the inputs. It covers all the inputs. And what you're gonna have then is that when you change anything in the transaction, you change any input or any output, the signature will not be valid anymore. And the signature is made for each input. So technically speaking, you could have a transaction that takes input from several wallets and outputs to several wallets. And that's the case for the transactions that mixers do. They combine several signers, several owners of funds, and then they mix the coins into several output wallets. So when when you sign a transaction, so when you sign a Zcash, um, one very simple design would be, okay, I send a Zcash to the ledger, and the ledger signs that. Right? You have you say, do you want to sign the Zcash? And then you press confirm. Okay, fine, I do that. And the wallet computes the signature based on the secret key that it has internally, and sends back the signature to the wallet, to the online part. But you can see that that design would has major flaw. And that personally, if you see a Zcash, there's no way to understand to see what it refers to. So the Zcash could be any Zcash. And if the wallet is compromised, if the online part of the wallet is compromised. So again, we're not talking about being able to compromise the ledger itself. We assume that the ledger app is bug free, and there's no security issue with the device itself. But we are assume that the attack vector comes from the online part, and the online part is external to our world. It means that somebody, because it's online, may have infiltrated your network and may have replaced your online wallet with a bad version. So it's possible that instead of it shows to you that it's sending coins to Alice, but actually it's making a transaction for Bob, and it's computing a Zcash paying Bob, whereas it shows it as paying as Alice. So you sign it without knowing that, and the funds now are gone to Bob, and no way to retrieve them. So obviously this design is really not that good, right? You can't send a Zcash and expect the user to verify that the Zcash is correct. It's completely impossible for the user to know. So the second and I would say the more natural design would be to send a whole transaction. So the whole transaction to hash is sent in clear to the device, to the ledger, and the ledger would be responsible for calculating the Zcash. Out of like a normal transaction, like 200, 300 bytes, that's not a lot of work. And even though these devices are not super powerful, it's still gonna be okay. Right? So you send that, and boom, transaction is at least you will see the ledger can show to you that the transaction is made for at least for a certain amount. Do you want to sign it? You say yes. The ledger calculates the Zcash, applies the signature, and then returns the transaction signed to the online wallet. So it seems to be okay, but actually there's a flaw, and the flaw is a bit much more subtle than before. The flaw it comes from the way that the transaction is formed. The transaction actually has outputs, and the outputs have destination, like they have, let's say, an address. Well, it's technically it's a script, but it's a redeem script. It's a pub script, uh, but 9 times out of 10 it's going to be an address. It's equivalent to an address because there are some standard scripts for that, right? So let's say that it's sending out to a particular person, put an address with a particular amount. So you can see that the ledger can display that on the screen. You can have the user validate that part before the ledger signs. But the issue comes from the inputs. So the transaction itself will have references to the inputs, and the references will be what was the transaction ID that created that output, and where, right? Which transaction and which output was it in that transaction? Because transaction can have n certain number of outputs. So we would say transaction blah 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 blah, some hex, and then output number 5. And that refers to a particular previously unspent output UTXO. The problem here is that unless you have the blockchain data, this information doesn't give you the amount that was on that output. So the possible malicious wallet will, just for the fun of it, take way more than necessary to make the payment. So for example, you're paying somebody 10 Bitcoin. So normally your wallet will take maybe like 11 Bitcoin in its input, make payment of 10 Bitcoin, and then a change of 1, right? Minus fee, something like that. But just to be annoying, you could make a transaction that has 200 Bitcoins as input, still pay at least for 10 Bitcoin. So you can see that 10 Bitcoin for Alice, and then you confirm that. But then the change is wrong, right? The change is not going to be, it's still going to be 1, but then the excess would automatically go to the miner. So all that funds will be lost. So you're going to spend 190 Bitcoin more than necessary. 90 Bitcoin more than necessary, because you're spending 100 Bitcoins, and you should have paid only 10 Bitcoins. So the problem that your device, your Ledger device, and that's the same as Trezor. I'm not picking up on Ledger or Trezor in particular. That's the same for any hardware wallet. The hardware wallet does not know the just by looking at the transaction, he does not know the amount that was spent on input. So these are considered untrusted inputs. To mitigate that issue, to resolve that issue, which is a very big issue, to be honest. Now the wallet has a different format for these kind of transactions, for Bitcoin transactions, where in addition to sending the inputs as required by the protocol, by the transaction protocol, it also sends the whole transaction that created that previous output that now is the input. So in this way, the wallet, the ledger, can verify the amount on that particular outpoint, hash the entire transaction, and verify that the transaction hash is identical to the one that was used as a reference. So you didn't cheat and you didn't send an unrelated transaction. So you can verify that you have shown the proper transaction, and then you can see that the amount on that output is as expected. But in doing that means that for every input of a transaction, now you're going to have to send the previous transaction, the transaction that created that input, in this entirety, the complete transaction that created that. So that's a lot of data to send around. I mean, it's better safe than sorry, I guess, right? So it's still better to do that than not do anything. But that's a concern. And now let's move on to Zcash. But now you should know and see the issue more. The issue more is that we want to make sure that the transaction is as expected by looking at what we really care about transaction as a user. We want to make sure that it's paying the right person or the right recipient, so the right address with the right amount, but also that we are paying the right fees. So we don't really care whether the inputs are where they come from, because even if they don't come from, the network will check that. There's no way for the transaction that is like trying to spend coins from some other person's wallet to actually be accepted by the network. And if it was, then that system is broken. So we don't really care whether it's going to be our coins, because it's going to be our coins on the transaction will fail. But we do want to make sure that it's not too many of our coins. So that's one aspect. And the second aspect is, again, that we are sending to the right people with the right amount. So if we make sure that this goal is achieved, then we can have our wallet or the Ledger app work as intended. So this is what the Ledger app should be able to verify when we send the data, when we try to form the signature on the device. So and that's okay. So let's go to Zcash and see that with Zcash it's also a bit harder because the transactions can also have shielded inputs and outputs. So again, inputs, we don't really care where they come from. We care about the amount. Outputs, we care about the address and the amount. So if the online part, if Y Wallet was sending the transaction, encrypted transaction to the ledger would not have any way to show to the user the recipient. So you won't be able to say, okay, you're paying at least here 10 ZEC. Right? So one design would be to send the transaction encrypted, but also send the key so that it can be decrypted. That's one way to do it. It's a bit convoluted. The other way to do it is to send the transaction unencrypted in plain text, and have the ledger encrypt the transaction. First, show the content of the output. So you see that it's paying Alice for 10 ZEC, and then encrypt it itself, and then apply the signature on the encrypted output. So that's more work, right? And again, because these devices are not super powerful, if you start having a lot of outputs, if you start having sizable transaction, this would take a while, and this may even run out of memory. So again, these devices are super low, very little memory. So fortunately, or not so fortunately, because it's really by design, the design of the transaction v5 transaction version 5 addresses these issues, right? And we see now how that works. So the transaction v5. Okay, let me pull the zip for that. I don't remember the number. 244. Transaction, yeah, it's 244. Okay. Yeah, so that's transaction ID and zip 244. So this defines this document defines the format for the transaction hash. So there are several transaction hash. There's a transaction hash for identifying the transaction. So this one has a property of not being malleable. So if you change anything, if you change the signature, you try to you cannot make another transaction that is identical to the first one without changing the transaction hash. Basically, anything that has a meaningful part in the transaction, so none of the witness data, will be covered by the transaction ID digest. But that's not actually the one that we care about. What we care about is the SIG hash, so the signature hash, the transaction the hashes that we need to use for signing the inputs. So that is also covered by this document. But let's see first how this stuff works. So you see that instead of having now one single hash to calculate over the entire data that you want to cover. So before, like for Bitcoin, you have inputs and outputs, and then you basically put everything into the hasher, into the hash machine, and then boom, it would bring you a hash value out. Right? So one go, one hash, that's it. So this guy is a bit more sophisticated, where it hashes different parts of the transaction. So for example, here you would have a hash for the transparent part of the transaction, another one for the sampling part, and another one for the orchard. And even in the transparent part of the transaction, you would have first a hash for the previous outputs, a hash for the sequences, and a hash for the outputs. So it's a tree of hashes, right? And at the very top, you would have the primary hash that is going to be used for signing. And one of the property of a tree of hashes, or tree of hashes means that this hash here is going to be obtained by hashing this, and this together, right? So it's a hash of a hash of a hash if you want. And the one of the property is that because hashes have pre-image resistance, if you change anything at any level of the tree, then the hash at the top will be completely different. And there's no way for an attacker to be able to replicate the top level hash while changing any part of that tree. So you cannot change, let's say, this part of the tree and compensate for that change by doing something here, for example, and preserve the resulting hash at the top. That is impossible by design of the hashing function. So if we have that value up there, it means that that value, a certain value, is the result of using the exact value for all the intermediate hashes. And one advantage of this is that you technically don't have to calculate the entire hash yourself. So if you have the transaction, if you have the entire transaction content, then you could go and then get the previous outputs, hash that, get all the sequences, hash that, and so on and so forth, and then combine this into the transparent hash, decode digest with the same as a hash. And then same thing as this, you have all these elements are part of the transaction, so you can pick them up and then hash them together, get all the intermediate hashes, and then combine this stuff, and then you would get the one. So this is essentially what the full node would do. It would do that because it has all the information. But when you send that to the ledger, you could be smarter, and you could be avoiding all this heavy computation by having the ledger only calculate the inner or the leaf digest, these are hashes that you care to lock in place. So let's say, for example, that you want to make sure that the sequence is the one that you expect the user, the transaction to use. So let's say that you really care that the sequence should be FF, 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 right? Should be that. And that if the wallet is compromised and send you any other value, you don't want to sign that transaction. Or you want to do, okay, you sign your transaction, but you're not going to sign the proper Zcash. And you're not going to sign the one that is going to be accepted by the network. So in terms of, in technical terms, what it means is that if the Ledger app will sign FF here, but if afterwards the wallet changes that to 00, then you will not be able to get the same SIG hash that the Ledger app had at the moment they signed. So in order to do that, I want to make sure that the FF is the proper sequence is used by the Ledger app. So I would use that in my calculation of the transactionality digest. But then for the other parts, for the previous outputs, I don't care. I can accept something from the online wallet. So the online wallet can send me what it wants for the outputs hash and for the previous outs hash. It can send me what it wants or whatever. Then I will calculate, I mean the Ledger app, I will calculate myself the sequence hash. Then I will combine the three guys together and calculate myself the transparent hash. Then I will combine with the header hash, sapling hash, and orchard hash that the the compromised online app sends me, right? And then once I get all these four things together, I will calculate the final transaction ID hash. So basically, I take this from myself. I take this from outside, this guy from the outside, this guy from the outside, and this guy from the outside. Right? And by taking these values from the outside, I will be able to calculate my own transaction ID digest. I will sign that, and I will return the signature based on that hash to the online wallet. Now, if the online wallet wants to change the sequence and puts like 0 instead, then he would in effect modify the top level hash. And again, even if he tricks me and by sending a different value orchard hash, there's no way for the app, malicious app, to reconstruct the same transaction hash that I use, the ledger I use to sign, because of the property of hashes. And this idea is a cornerstone of Merkle proofs. This is actually called a Merkle proof. This is a Merkle tree, a tree of hashes, and what we have been describing is a Merkle proof. So our wallet design for the Ledger app is that we are going to use Merkle proof to make sure that we have received enough, we are locking in place the information that we have to enforce. We want to enforce that the amounts are correct, so the fee is correct, and that the recipients are correct. So how does that translate? Obviously, we don't have orchard, so this whole thing here is gone, right? We're never going to have orchard. We are impacted in the sapling outputs, right? Because sapling output will be the shielded outputs. So who we pay on the shielded output would be there, and it would be there. Normally, all this stuff is encrypted, right? So this stuff, if you look at the information here, this is based on the encrypted part. And obviously, we don't want to do the encryption really ourselves, but we still want to make sure that the encryption that is made cannot be compromised, cannot differ from the information that we are showing to the user and that the user has validated. So the user is going to see a destination, a recipient address, a Z address, and an amount. Then from that, we can calculate. So we, again, is the ledger. We calculate the node commitment. So that's the node commitment is a special form of hash covering the address and the amount, right? So we cover that with the node with the node commitment, and that node commitment is part of the sapling spans compact digest. So we're gonna get that here. So we want to compute that ourselves. We receive all the destinations. We calculate all the node commitments, and then we calculate the not span, sorry, the sapling output compact digest, right? So this is the one thing we calculate ourselves. And the second thing that we calculate ourselves is the amounts that are inside this part here. So it's actually not this part, it's a part for transaction ID SIG digest. So you can have it down there. When you're signing for transaction, when you're signing, the ID differs from the ID used for identifying. So this is T. We have to go to S, right? Signature digest. So signature digest has this part here, transparent signature digest, and the difference is that the transparent signature digest has the amounts, whereas the other guy didn't. So we want to make sure that the amounts on the transaction inputs are correct, and we also want to make sure that we are paying the right people, right? So we're also going to cover that guy, the output signature digest. So we calculate that ourselves, and that ourselves, right? And the sapling output compact digest ourselves. Right? So these three guys we compute ourselves. Then we get all the rest, all the So this guy, this guy, this guy, this guy, like all the other things, plus the ancestors, so exactly the same technique I've shown you before, in order to calculate the top level signature digest, and then we're going to sign on that. So this is, in a nutshell, the protocol, the security protocol of our Ledger app with respect to the online wallet. So now, if you think about it, if the online we can scale to an arbitrary size of transaction. So even if the transaction has 1,000 inputs and 1,000 outputs, the amount of memory that the Ledger app is going to use is going to be exactly the same. It's going to take much longer, of course, right? But the time it takes would be proportional to the amount of inputs and outputs, and not to the square. If we were going for the more simple design, so it would be proportional to the the transaction size, input and output size, and but the amount of memory will actually be exactly the same, because when we calculate the, for example, we calculate the amount seek digest, which is a hash calculated on based on, let's take a look at this one. It's the what's the black to be, right? Is the hash of the concatenation of the 8-byte signed Little Indian representation of all value fields for the coin spent by transparent input of the transaction. So what it means here is that we take all the inputs value, we put them into the hasher, and then we get one hash value. So we don't need to have all these values in one go, right? We can have the online wallet, we can have Y wallet send transaction inputs one by one, and then we take these values and we put into the hasher. The hasher has a constant size memory usage. It's 64 bytes. So we call it a bit more than that, but it's a constant size for regardless of how many bytes you send in. So even if you want to hash a megabyte of data, as long as you throw in that megabyte of data little by little, then the current state of the hasher will be the same. And at the end, we take the final hash value, and that would be our amount seek digest. And the same thing applies for the other components. If you go smart about it and you don't like buffer the entire transaction beforehand, you can have the Y wallet, the online wallet, stream in the information, have the Ledger app compute, progressively compute these digests, these internal digests, internal hashes as they come. And then when the transaction is finished, finalized, then these we send the Y wallet, we send the Merkle proof, the other side of the of the hash tree, right, or the other branches of this tree, and then the Ledger app will also combine this stuff, these hashes together, in order to form this one. And then this tree here has a fixed size regardless of how many inputs and outputs you have, because each branch here is essentially a hash value. So it's always like 32 bytes. So we got to a point where you can see that the amount of work is really proportional to the number of inputs, because hashing is proportional to the number of inputs. Then calculating the seek hash is also then proportional to the amount of inputs and outputs. And then at the end, signing is also proportional to the input and outputs, because for each input you would have to apply you would have to calculate one signature, and that signature is applied on the seek hash with a constant time. So it's just a elliptical curve calculation, which does not vary with the value of the seek hash or the value of the secret key. So all in all, you can see that everything is proportional to the number of inputs, which is really not obvious if you take into consideration the complexity of making these transaction signatures. So the whole thing is proportional in time to the size of the transaction, And oh, but even better, it's constant memory usage, regardless of the size of the transaction. Obviously, not the case for the online wallet. Why wallet would have to do more, but it doesn't matter because why wallet has a lot of memory and has a lot of computer resources. Right? So we don't care about the online part. We really care about the ledger side in this in this video in this discussion. All right, so I hope that that will explain the design of this explains the design of the ledger app Zcash versus the previous design that Zondex has achieved has used. And to their defense, this is only possible because uh, transaction v5 is out. Transaction v4 is not using a tree of hashes, so this stuff is not possible. But now that we have v5, it's it would be a very well, it would be very inefficient to use not use v5 and still rely on v4. All right, and also I think that this is a good reason to adopt v5, even though it had created a bunch of issues because some of the wallets are not updated and they are not able to understand the v5 format. But as you can see, the v5 format brings um, very good scalability improvements to the Zcash protocol. All right, that's it. That's all for today. And again, if you have any question, please feel free. And I hope that this app is making good progress, but you can imagine that it's actually pretty hard. So don't it will take some time before it is ready. So until then, cheers.